Here's an equation. X squared equals minus 1. What are the solutions? Well, if we stick to the regular numbers, the real numbers, there aren't any solutions. Mathematicians invented I to be one solution. You can use I to solve other equations. For example, x squared equals minus 9. The solution is 3 times I. Now, numbers such as I minus I, 3 times I, and so on, are called imaginary numbers. You can use the imaginary numbers to solve other equations. X minus 1 quantity squared equals minus 9 has the solution 1 plus 3 times I. When you add a real number to an imaginary number, you get a complex number. A complex number has a real part and an imaginary part. The complex number is the real part plus the imaginary part times I. So both real part and imaginary part are real numbers. Let's try working with complex numbers in Python. Instead of I, Python uses J because in electrical engineering, I traditionally means current. We enter the imaginary number 3J, and Python says, yeah, I got it. If you enter just J by itself, Python thinks you're referring to a variable. So instead, we can type 1J. Now, we can use the usual arithmetic operations, such as plus, minus, times, and divide. And they work pretty much as you'd expect. Note that adding two complex numbers means separately adding their real parts and their complex parts. We can check our solution to x squared equals minus 9. That works out. We can extract the real and imaginary parts of a complex number using a dot notation. X dot real, x dot imag. Now, this may remind you of object-oriented programming and access to instant fields. Yep. Complex is a class in Python. We see that in Python you use plus to add real numbers or complex numbers. Use of the same name for different procedures is called overloading. And overloading turns out to be quite useful. Let's write a procedure, solve, to solve the equation ax plus b equals c. Well, this is straightforward in Python. And we can use this to solve an equation like 10x plus 5 equals 30. Right? We plug in the numbers and we get the solution. But because of Python's use of overloading, we can use the same procedure to solve an equation that involves complex numbers. We just plug in the same complex numbers and we get the solution, also a complex number. So the same procedure that we defined for real numbers happens to work for complex numbers as well. When we want to refer to a field without specifying exactly which field, we'll use this notation with this blackboard F. So why does this procedure give the correct result for complex numbers as well as for real numbers? It's because it's just based on a few simple facts about the arithmetic operators. For example, division is the inverse of multiplication. Subtraction is the inverse of addition. Similarly, much of linear algebra is based on a few simple facts about the operators plus, minus, times, and divide. Division is the inverse of multiplication. Subtraction is the inverse of addition. And other algebraic properties such as that addition is commutative. The order doesn't matter. And multiplication distributes over addition. So you can plug in any collection of numbers with their own arithmetic operators, plus, minus, times, and divide. And as long as these satisfy these basic algebraic properties, you can do linear algebra with that kind of numbers. A collection of numbers that has these properties is called a field. So we're going to study three fields in this class. The field of real numbers, because that's a very familiar one. The field of complex numbers, and the finite field, which I call GF2, which consists just of 0 and 1. And here's why we're studying the complex numbers. For one thing, the set of complex numbers is very similar to the set of real numbers. So we can experience this idea of abstracting, of generalizing, of choosing different fields without it being that different. Now, another reason that complex numbers are convenient is that they're built right into Python. Also, complex numbers are in some sense the intellectual ancestors of vectors. So some of the basic operations that we can do with complex numbers we'll later learn how to do in higher dimension with vectors. And finally, in more advanced parts of linear algebra, complex numbers are essential.